Hello, good people. Welcome to the video number one of topic section 10.11 or 10.11. So this technically is a topic that comes before the previous set of videos, but I like to put out the power series idea first and then talk about a specific type of power series. And so we're going to be looking at some approximations in this set of videos, but then we're going to extend that into some series, some power series. So let's kind of think about what we've done and how that's going to connect to where we're going. So if you read this part, this is just reminding you that in the first semester when we were doing linear approximations, we were using this formula to figure out the equation of the tangent line. So this right here, and I'll do it in blue. So this is the equation of the tangent line. Now, we in this class perhaps wrote it like this. But m is my derivative, and it's my derivative at a specific point, right? So a specific x value, which I'm calling c, times x minus that x value plus my y value, which is the function value at that point. And so if you look at this blue box and this written the way we used to do it, it's kind of telling us the same thing, right? The idea that I can build a tangent line to approximate. And here we see a pretty good representation of what's going on. F is the function, and L is my tangent line. And as you can see, if I were to zoom in, when I'm on this point, and this is something that maybe we didn't stress enough, what's special about this line is that this line shares two things with the curve. It shares the same y value, right? This green point has the same y value on the red line as it does on the blue line, and it shares the same slope. The slope of the curve at that one green point is the slope of the red line. So with these two concepts established in common, we say that, well, if we go a little bit farther this way, and how much farther we're talking about, that's debatable. But if you move this way and I go up to a point on the curve and I go up to a point on the line, they're pretty close to each other, right? Or if I go this way, and let's say I go up to a point on the curve and I go up to a point on the line on that x value that I chose, they're pretty close to each other. So I can approximate, excuse me, I can approximate blue curve function values with red linear values. That's the whole idea behind approximation, is that we can approximate complicated function curve values with simple linear values. Why can we do that? Because we created a line that shared some characteristics with the original curve, which is same y value and same slope. And so when we get to, and we'll do a quick example here. And in example one, they want us to find a linear approximation to this function at x equals 1. We can do that because we can find the slope formula, the derivative of natural log is 1 over x, and we can find the slope at 1, that's 1, so this is my slope. I have an x value, I don't have a y value, but I can figure it out because if this is x, that means my y value is f of 1, which is the natural log of 1, which is 0. So now I have everything I need. So y equals my slope, which is 1, times x minus my x value, plus my y value, which is 0. Do I need the plus 0? I don't. But this is what I have. Great. So when I go to my calculator and I graph the natural log of x, and we'll set a nice window. Let's see if we can see it. There you go. And now when I create my linear approximation that I just did, 1 times x minus 1 plus 0. If you want to put the whole thing, you can put it that way and graph that at the same time. Right at x equals 1, hey, that's a pretty good approximation for the curve. If I were to zoom in right here, and I'm going to zoom in right there. Let's zoom in. Yeah, let's zoom box. So I'm going to zoom in pretty close to that intersection point. So what this box does is it's going to zoom in. Oops, I went too far. I'm going to zoom in that area. Press enter. And we can see, gosh darn it, that's pretty darn close. We know that they're exactly the same here, but this is pretty close. And even here, this is pretty close. So they're pretty good approximations. So in example 1, that's what we did. But the question now comes in part B, could we create an even better approximation? Could I create a quadratic approximation? Now, what would that mean? Well, if I go back to my graph here, that means I would create a curve that does a better job of hugging, if you will, getting really, really close to this blue graph. Right now, I notice there's a gap, right? There's a gap between the red line and the blue curve. But what if I created a red curve that was even closer and it mimicked the curvature of this? That would be an even better approximation. But how do we do that? Well, if we want the curvature to match as well as the slope, as well as the function value, then what we really need to have is a common second derivative. So just like we found the derivative here and substituted the 1 in there, we're going to find the second derivative. So why do we do that? Because I want the curvature to also match. So not only do I want my function to be the same y value, I also want it to have the same slope, and I want it to have the same curvature or concavity. So what we're going to do is create a formula that follows this pattern. What do I need? Well, I need the first derivative and I need the second derivative. And I need to evaluate those at the x value given. So we already know what this is. Natural log of 1, that's 0. We already know what the first derivative of 1 is. That's 1 over x, or 1 over 1, and that's 1. But now I need to find the second derivative at 1, which means I need to find the derivative of this first derivative that I got. Okay, well, that's easy. That's going to be f double prime of x, according to this. F double prime of x is negative 1 over x squared, which means when I come over here, the second derivative at 1 is negative 1 over 1 squared, which is negative 1. Great. What does that mean? That means I now have enough information to create this quadratic approximation. So how do we do that? Well, follow this formula. This formula says start with, let me do it in a different color here. Start with, so this is P2 of x. 2 because we're going to the quadratic second power, equals f of c, so that's f of 1. I'm just going to write it out first. F of 1 plus f prime at 1 times x minus c plus f double prime at 1 over 2 times x minus c squared. Now, I do want to acknowledge that I'm using this formula without proving it. You can look at the proof and how we got there by reading this part and following the colored, or in your case, non-colored lines here for P2C and P prime and all that stuff. You can do that. But I'm accepting the fact that this formula here is a way for us to find a better approximation, and that would be a quadratic approximation. So f of 1, we already found that, that's 0, plus f prime of 1, that is 1 times x minus c, plus f double prime of 1, that's negative 1 over 2, well, it's negative 1, and then we're going to put it over 2 times x minus 1 squared. My bad. My c value is the point at which I am centering my approximation. So I'm looking at x equals 1, so that should be centered at x equals 1. So just to make it a little bit nicer looking, we're going to say this is x minus 1 minus 1/2 x minus 1 squared. So I'm claiming that this equation, which is a quadratic equation, is going to be an even better approximation than the linear equation that we drew. Is it? Let's find out. I'm going to go back to my equation here. I'm going to turn this one off. And then here, I'm going to go ahead and type in what we got. And what we got was x minus 1 minus 1/2 of quantity x minus 1 squared minus 1/2 times quantity x minus 1 squared. So remember, natural log is my original function. This quadratic is supposed to create a better approximation. Let's see. Here's the curve, the natural log function. And here is that quadratic curve. It has curvature, and the curvature is matching even better than the linear function. And you'll notice that, I know I can't write on this. Oh, maybe I can scoot it in here. Let's see if I can do this. I'm not sure I can, but I'm going to try. Can I? There it is. Ha! So notice that the curvature is so much closer. As a matter of fact, I can say that maybe up to here and up to here, like that's, or maybe, yeah, maybe up to here. That's a pretty good approximation. Like they're almost identical, right? And I guess I want to show also that when I look, when I graph this, and let's see if I can do the same thing over here. Oh, there it is. Nice. So notice notice how close the line is. I'm going to say maybe like here, from here to here, the line in red and the curve in blue are almost indistinguishable, right? They're pretty close to each other. They're right on top of each other. But when I look at the curve in black with the curve in blue, that line changes out even more. Like they're indistinguishable on a bigger window. And so the idea is, can I continue to do that? And that's what we're going to explore in the next couple of videos is, can we create better and better approximations by just continuing to take derivatives and adding more terms in my polynomial? And we'll come back in the next part and we'll introduce formally Taylor polynomials as a way to approximate a function.